9. Settle down. Settle down. Let's dive into our new chapter today, which is all about motion. We see things moving all the time, right? Cars, people, even the earth itself. But what exactly is motion? And how do we describe it? What is motion and rest? First things first, motion means an object is changing its position compared to its surroundings. Think about it. If you're on a bus and it's moving, the person sitting next to you isn't moving relative to you. You're both in the same moving box. But to someone standing outside the bus, both of you are definitely in motion. So motion is always about who you're comparing yourself to. And rest is just the opposite. An object is at rest if its position isn't changing relative to its surroundings, like a book on a table or a stone sitting on a hill. They're just chilling there. Distance and displacement. Not quite the same. Now, when something moves, it covers some ground. We measure this in two main ways: distance and displacement. Distance is simply the total length of the path you actually travel. Imagine walking from your home to school. You might take a winding road, go around a park, maybe even stop for a snack. The total length of that entire path is your distance. Distance only tells you how much you traveled, not where you ended up. It's a scalar quantity, meaning it only has magnitude, a number and a unit, like 500 meters. Displacement, on the other hand, is the shortest straight line path from where you started to where you ended up. So if you draw a straight line directly from your home to your school on a map, that's your displacement. Displacement tells you both how far and in what direction. It's a vector quantity, meaning it has both magnitude and direction, like 200 meters northeast. Both distance and displacement are measured in meters in the SI system or centimeters, cm in the CGS system. Speed and velocity, how fast and where to. Next up, we have speed and velocity. These also seem similar, but they have a crucial difference. Speed is how fast an object is moving, without caring about the direction. It's the distance covered in a certain amount of time. Formula: speed equals total distance covered / total time taken. For example, if you run 100 meters in 10 seconds, your speed is 10 meters per second. Like distance, speed is a scalar quantity. It only has magnitude. Velocity is also how fast an object is moving, but it does care about the direction. It's the displacement in a certain amount of time. Formula: velocity equals displacement / time. So if you run 100 meters east in 10 seconds, your velocity is 10 meters per second east. Velocity is a vector quantity. It has both magnitude and direction. Here's the cool part. If you're moving in a straight line without changing direction, your speed and the magnitude of your velocity will be the same. But if you move in a circle or a zigzag path, your speed might be constant, but your velocity is constantly changing because your direction is changing. You can change an object's velocity in a few ways. 1. Change its speed, keep direction same. A ball falling under gravity speeds up, but keeps going straight down. 2. Change its direction, keep speed constant. Think of a car going around a roundabout at a steady speed. Its speed isn't changing, but its direction is, so its velocity is changing. 3. Change both speed and direction. A football kicked into the air curves and slows down as it goes up, then speeds up as it comes down. Acceleration. The change maker. What happens when velocity changes? That's when we talk about acceleration. Acceleration is the rate at which velocity changes over time. Formula: acceleration equals change in velocity / time. If your car goes from 0 to 60 kilometers per hour, it's accelerating. If it brakes, it's also accelerating, but in the opposite direction. We call that deceleration or negative acceleration. The SI unit for acceleration is meters per second squared, meter per square second. Like velocity, acceleration is a vector quantity because it has both magnitude and direction. Understanding motion with graphs, we can visualize motion using graphs. A common one is the distance-time graph. In this graph, we put time on the x-axis and distance on the y-axis. If an object is in uniform motion, meaning it covers equal distances in equal time intervals, like a car on cruise control, its distance-time graph will be a straight line. The slope of this straight line tells us the object's speed. If an object is in non-uniform motion, meaning it covers unequal distances in equal time intervals, like a car in city traffic, its distance-time graph will be a curved line. Uniform circular motion. Going in circles. What if an object moves in a circular path but keeps a constant speed? This is called uniform circular motion. Examples include the moon orbiting the Earth, an electron moving around the nucleus, blades of a fan spinning at a constant speed, Even though the speed is constant, the velocity is constantly changing, because the direction of motion is always changing as the object moves around the circle. Newton's laws of motion. The rules of the game. Now, let's get to the superstar of motion, Sir Isaac Newton, and his 3 amazing laws. Newton's first law of motion. The law of inertia. This law is all about inertia. Inertia is an object's tendency to resist changes in its state of motion. Basically, if something is still, it wants to stay still. If something is moving, it wants to keep moving at the same speed in the same direction. Newton's first law says, an object will stay at rest or keep moving at a constant velocity in a straight line, unless an external, unbalanced force acts on it. Think about it. Inertia of rest. When your bus suddenly starts, you feel a jerk backward. Your body wants to stay at rest, but the bus moves forward, so you feel pushed back. Inertia of motion. When the bus suddenly brakes, you lurch forward. Your body wants to keep moving, but the bus slows down. Inertia of direction. When a car takes a sharp turn, you feel pushed to the side. Your body wants to keep going straight, but the car turns. That's why mudguards are fitted to vehicles. Mud flies off tangentially due to inertia of direction. What is force? So what causes these changes in motion? A force. A force is anything that can change an object's state of rest or uniform motion. It can push or pull. Forces have both magnitude, how strong, and direction. Forces can be balanced or unbalanced. Balanced forces. If forces acting on an object are equal in magnitude and opposite in direction, they cancel each other out, and the object stays at rest or continues moving at a constant velocity. Like a book resting on a table. Gravity pulls it down, the table pushes it up, and they balance. Unbalanced forces. If the forces don't cancel out, there's a net force, and this unbalanced force causes the object to accelerate, change its velocity. When you kick a football, you apply an unbalanced force, and the ball moves. Newton's second law of motion. Force, mass, and acceleration. This is where we connect force to momentum, which we discussed at the beginning. Newton's second law states, the rate of change of momentum of an object is directly proportional to the applied unbalanced force and takes place in the direction of the force. In simpler terms, the more force you apply, the faster the momentum changes. The bigger the change in momentum, either by changing speed or mass, the bigger the force involved. Think back to our bullet example. When a bullet is fired from a gun, a huge force is applied for a very short time, giving the small bullet an incredibly high velocity, and thus a huge momentum. When this high momentum bullet hits the plank, its momentum changes very quickly, creating a massive force that pierces the wood. When you throw a bullet by hand, you apply a much smaller force. The bullet gets a much lower velocity, and therefore less momentum. When it hits the plank, the change in momentum is less, so the force exerted on the plank is also much smaller, hardly scratching it. Momentum, P, is simply mass, mx velocity v. It's a vector quantity, measured in kilogram meter per second. Newton's third law of motion. Action-reaction. This is a fun one. Newton's third law says, for every action, there is an equal and opposite reaction. This means forces always come in pairs. You can't have a push without something being pushed back. When you push a wall, action, the wall pushes back on you with the same amount of force in the opposite direction, reaction. That's why you don't go through the wall. When a rocket blasts off, it pushes gases downwards, action, and the gases push the rocket upwards, reaction. Law of conservation of momentum. Finally, we have the law of conservation of momentum. This is a very powerful idea. When no external force acts on a system of 2 or more interacting objects, their total momentum remains constant. Imagine 2 billiard balls hitting each other. Before they hit, each has its own momentum. When they collide, they exert forces on each other. Newton's third law. After the collision, their individual momentums might change. But if you add up the momentum of both balls before the collision, it will be exactly the same as the total momentum of both balls after the collision, provided no outside force, like friction on the table, interfered. This law is fundamental to understanding collisions, explosions, and many other phenomena in physics. So that's our big picture of motion class. We've covered what motion is, how we measure it, what causes changes in it, and the fundamental laws that govern all movement in our universe.